Hello everybody, and welcome to our short talks or our final event of the Open Doors weekend, our virtual Open Doors weekend here from the Royal Observatory in Edinburgh. I'm so glad that you can join us. If you are watching and you want to tell us where you're watching from, we love to hear that. Please do use the chat button. I can see that some of you have already found the chat button. Hi, Tracy from Lincolnshire. Lovely to have you with us. So yeah, do say hello in there. Also, if you've got any technical problems, kind of general questions about this event, pop those in the chat as well, and we'll do our best to answer those for you. Another button that you can use is the Q&A button on your screen. So we'll have 4 speakers today, and if you've got any questions for the speaker during their talk, press the Q&A button, and after the talk, Brian, who's just in the background at the moment, will be helping us field some questions, ask some questions of our speakers. I should say my name is Fiona, and as I said, we've got 4 speakers. They'll each be taking 15 minutes and about 5 minutes for questions. And we've got lots of topics, lots of exciting things to get through, engineering and astronomy. So I think we should get to it and get started. The final thing before we start actually is just to let you know that there is a live transcript. You might have noticed if you've got it turned on, that it's auto-generated, so it's not perfect, but you can use that if you like. So if you press the live transcript button, you can show and hide subtitles, and you can change the size of them as well. This has been recorded. We're live streaming on YouTube as well, so hello if you're watching on YouTube, and this recording will be up on YouTube a little bit later, well, straight after this actually, so you can share it with other people as well. So our first speaker for today is Trent Dupoy, who is hopefully waiting in the background. Hi, Trent.
Hello.
Hello. How are you doing?
Just another nice warm day here. So.
Yeah, I mean, it's surprisingly warm here in Edinburgh. I don't know about where everybody else is, but I thought I was kind of getting jumpers and boots out and things for winter, but not quite yet. Yeah, summer's hanging on, which is nice though. Nice to have some sunshine, right? So are you okay to get started on your talk?
Yes, yes.
Oh, you're talking about rogue planets, which is
that's right.
intriguing.
So yeah, so my screen looks very interesting. Does the slide looks okay?
Yeah, it looks good to me.
Okay.
Hang on,
yeah.
It's gone a bit funny. It's gone kind of a different pattern. Oh, that one's okay. It's okay now. It was maybe just
yeah, it glitched on mine as well. I don't know what just happened.
Fingers crossed.
But yes, hello. I am going to talk about sort of a interesting thing that is out there that is a part of some of the work that I do here at the ROE, and that is the fact that there are planets out there floating around in between the stars, and we occasionally find them. And I'm talking about exoplanets. I realized as I was just starting to prepare this that probably many of you are familiar with some interstellar comets that have come through the solar system. That's when the planets come to us. I'm going to be talking about stuff that we see out there that hasn't ever visited the solar system. So of course, planets normally are orbiting a star. In fact, the IAU, the International Astronomical Union, defines a planet as something that orbits a star. So technically, things out there wouldn't be considered planets today, but they could have potentially been part of a planetary system in the past. So how do we? So many of you may be familiar with the fact that we have many different ways of detecting planets around other stars. I put direct imaging at the top because that's the one that is most related to what I work on. On the bottom, there are 3 other methods: radial velocity, which is also known as the Doppler method, and transit photometry. I'm not going to go into details about these, or microlensing. Actually, microlensing is using the fact that mass bends light to detect small amounts of mass of planets around other stars. In principle, microlensing can also find rogue planets because all it cares about is detecting mass, and that mass doesn't have to be orbiting a star. Radial velocity and transits, of course, they require they need to be orbiting a star for you to detect them. So what I'll be talking about today, for rogue planet purposes, I'm only going to talk about stuff that's sort of directly imaged. But I just mentioned that there is starting to be some growing evidence from microlensing that there may be populations of planets going around. And I'll motivate the reason of focusing on direct imaging, not just because that's my particular field, but because that's the stuff that's nearest to us. So here's a schematic of the Milky Way, the galaxy we live in. And the stuff I'm going to be talking about today is all the region of space that's immediately around us. Whereas things detected with microlensing, if you ever see stuff about this in the news, that stuff is way towards the galactic bulge, way far away from us. It's still really interesting because it tells us, it'll give us statistics about what sort of planets are out there. But as far as things that are in our neighborhood, that's only going to be from direct imaging. So, brief reminder of what direct imaging of exoplanets is. You block the light from the star and as much as possible in an effort to see faint things orbiting it. What the light we're detecting from these planets is, at least everything that's been done so far, is not reflected light, like you might imagine, but the planets actually are luminous themselves. And so they're glowing. And so most of this work is done in the infrared because that's where they are, because you can detect heat very well in the infrared. So this slide just shows you a picture of myself taken with an infrared camera. You can see at the time I had a beard, so the hair is a little colder, the cheeks and the nose are hotter, and we see that we can do the same sort of thing with planets in the solar system. That's Jupiter in the bottom right. And so the reason we're putting off infrared light is because we're warm. Planets like Jupiter, they have their own heat. They also reflect light from the sun, but they're hot on the inside, just like even the Earth is hot on the inside. We have magma under the crust, not because the sun has heated up the planet, but because the Earth has its own innate heat. So this heat allows us to actually see planets, whether they're orbiting a star or not. So if we're going to talk about rogue planets, these would be things floating in between the stars. And here's just an image from some of the data that I've taken on this sort of work. And I can tell you there is a potential rogue planet in this image, but you would have no idea which of these points of light it is. So how do we actually go about telling what are the points of light in the sky that might be rogue planets? The key thing is we have to differentiate between planets and just other faint things floating around in the galaxy. So the first thing you have to ask is whether something is truly faint. Things can appear faint, but they might be just brighter objects that are farther away. That's step one. And then once you've established that it is actually intrinsically very faint object, how do you distinguish it from other things that are out there, like very faint stars? So this is the how faint is it thing is, again, you need to be ruling out the fact that it appears faint just because it's very far away. You want to establish that it's actually quite close to us. And to do that, you have to measure the distance to the object. And so for things near us, we can directly measure distances using the parallax effect. And what we do is you take data at different seasons of the year, and you use the Earth's orbit to allow you to see from different vantage points millions of miles apart, and then nearby objects will appear to move with respect to background objects. It's a little bit like this, it's the same exact effect that's used to make 3D movies. You have cameras in slightly different positions recording the same frame, and then when you put your 3D glasses on and you only look at, and your eye is only allowed to see one or the other, you're actually seeing that depth. And so it's kind of the same thing as seeing depth through 3D movies. There's a really nice animation that's been made by the Gaia space mission showing this, and I'll just show a bit of this movie illustrating the parallax effect. So what this movie is going to show is just one patch of the sky, and this is what if you magnified the parallax effect by 100,000 times, this is what you would see in the night sky as over the course of a year. stars moving around. And then they're about to connect the dots here with some familiar constellations, just to show you sort of, some of the stars in the constellations are much closer than other ones. So, just this idea of when you're looking out in the sky, some stars, even though we put them together in these constellations, there can be at very, very different distances. So anyway, this is the sort of thing that we use to measure distances to, and now I'm gonna have to get out of this movie. Yes. So let's say that, you've measured the parallax to one of these things with some infrared imaging. You've established that it's faint and close. Now the question is it really a planet or not? And so this has to get into the question of how faint can non-planets be? There's stars, and then there's things that are sometimes called failed stars, which are brown dwarfs. And you're probably familiar with the fact that stars come in many, many shapes and sizes, all the way up to supergiants that turn into supernovas and all that sort of thing. But there's a bottom end of stars, and that's when you can't fuse hydrogen in your core to shine, that's when you're a brown dwarf, and those things fade with time, sort of like planets do. And so this is the question is, you have to distinguish between these things and planets. Basically, a lower mass thing is going to be, so a planet is going to be fainter than something more massive at a given age. And so this diagram is just sort of illustrating how this works. Everything, planets and brown dwarfs and even some stars, fade with time. Stars eventually stabilize in their brightness. Brown dwarfs don't. And so you have this mix, if you just measure brightness, you could be confused between a young and bright planet or an older brown dwarf. And so you need this to break this information, break this degeneracy. So you have to know the age of the system as well. So I'll just give you an example of one of these rogue planets that's been identified. This is Psoj 318. This is an image of it in just the snapshot of the sky. We measured its distance, confirmed that it is faint and nearby. The way we're able to determine its age is because it's moving with a group of other young stars. And how we measure the age of those young stars is a totally different topic, but we know it's part of this very, very young group that's only a couple tens of millions of years old, which is young for astronomy terms. And then combining this brightness and the age, basically we consult something that looks like this diagram here. You measure the brightness, you measure the age, and you can infer what the mass is. And we found out that it's about 6 times the mass of Jupiter. So it's a giant planet. And more giant than any of the planets we have in the solar system. And it even shows huge variations in its brightness, indicating that it has storms and weather on its surface, which is very different from you would expect from a star, or even most brown dwarfs don't have that. So where, we occasionally find these things. Where do they come from? We don't really know, but there's 2 possibilities. One is that they could be ejected planets. And this movie on the right is an actual simulation of our solar system, where some groups have proposed that we started with 5 giant planets, not just Jupiter, Saturn, Uranus, and Neptune. There was a 5th one out there. And if you invoke this 5th planet, it can explain some of the things we see in the solar system, such as the distribution of Kuiper belt objects out around the orbit of Pluto, as well as the orbits of some of the giant planets. We don't know if there was a 5th planet in the solar system or not, but if there were, then that planet is out there as a rogue planet somewhere. So that's one possibility, that rogue planets come from ejected planetary systems. Or it's possible that nature just makes stars, essentially tiny, tiny, tiny stars. This is just a picture of one of these famous stellar nurseries, and it's quite possible that in this dark material here, there are things forming that are Jupiter mass. We don't know this part. We really don't have the information yet, but that's one of the things that the James Webb Space Telescope, with its being able to go so deep in the infrared, it'll actually be able to peer into these stellar nurseries and find things as faint as Jupiter possibly being born. And so we'll actually have this question we'll be able to answer pretty soon. So like I said, and possibly they could come from both of these sources. So we don't exactly know where they come from, but they're out there. This is a fun NASA Exoplanet Travel Bureau poster that has been made for one of these rogue planets, Psoj 318. And these travel bureau posters are promoting these exoplanets as if you could visit them. And the catch with the rogue planets is, there's no star, so the nightlife never has to end. All right, thanks.
Cool, thank you so much, Trent. That was brilliant, thank you. Sorry, I was just getting a poster and then you just ended really suddenly and I was like, oh, wake up, brilliant. So that was fantastic, thank you. So do we have any questions, Brian?
No, we don't have any questions yet. So I'll remind people, please do feel free to take advantage of the Q&A button at the bottom of Zoom to ask any questions you might have. And while we give people a chance to ask any questions, I'll just ask some of my own. So Trent, you mentioned brown dwarfs briefly as something kind of between planets and stars. Could you explain what brown dwarfs are?
Yes, thanks, Brian. Yeah, the reason stars shine is because they're so massive that the crush of the weight of the star, it creates super high temperature and pressure at the core of the star. That's enough to kick off nuclear fusion and turn hydrogen to helium, which releases energy, which then supports the star further and allows the star to just do that for billions of years. If you reduce the amount of mass, the crush at the core of the star is not high enough to reach that pressure and temperature that you need. And so fusion never kicks off, and so the star doesn't ever produce any new energy, so it just fades. And that happens around 70 or 80 Jupiter masses, so really massive compared to planets. And so that's why it just so happens that cutoff is quite high compared to planets. So there is this gap between things that we think can form like planets and things that form like stars. And so there's a huge range of these things right in between stars and planets.
Okay, thank you. We've got a few questions now, so I'll go through them as we have time for, and any other ones we can answer in chat. So the first question comes from Alec, who asks, what is the furthest planet that you have detected so far?
That's a good one. Personally, probably I'm trying to think. I think only about 30 parsecs or so, which is like 100 light years, which is really close compared to what so many people here at the Royal Observatory work on. 100 light years is nothing.
Sorry, Trent, I'm laughing because you say 100 light years is like really close. I'm just astronomy is it's another world, isn't it?
Yeah, space is big.
Pretty far.
Okay. So the next question comes from Roger. Do we have any idea of the numbers of rogue planets?
So there have been varying claims. A few years ago, some microlensing groups claimed that there was at least one rogue planet for every star in the galaxy. That number has come down. Well, they have since kind of realized that was maybe an overstatement based on better data. But I will say that it is a really interesting question. In the solar neighborhood, we have the coldest brown dwarf that is known. Actually, it's a planet, it's a rogue planet. The coldest rogue planet that we know is only 2 parsecs away. So it's basically, it's the 4th or 5th closest object to us, to the sun. And if it were just a bit farther away, we wouldn't be able to detect it. So that detection suggests that there could be a huge population of really cold rogue planets that we only have detected one because it's really close to us. So, it could be in that range of 1 per star, or maybe it's something like 1 per 10 stars, right? It's hard to say with what we know.
Thank you very much, Trent. That's all the time we have to answer questions live. So Trent, if you wouldn't mind typing in the answers to any of the remaining questions, and we'll move on to our next speaker.
All right, thank you very much, Brian. So thank you, Trent. I really appreciate it. Telling us about your research. That was really interesting. So moving swiftly on, we have our next speaker, who is James Aird, who I can see. Yep. Here we go. Hi, James.
Hi, Fiona.
Hello, how are you doing?
I'm good.
Good. So you'll be talking about the X-ray sky, hot gas and black holes.
That's right.
Okay, so whenever you're ready, if you've got any slides, if you could share your screen, and we'll get started.
Okay.
Do you need a hand? Are you okay?
It's slightly different to what I was expecting to be seeing. So
do you see a share screen button?
Yeah, I've got that. It's just not coming up with my desktop. So does that work? No. Failed to try again.
Do you want us? We've got one of our later speakers, Martin, say, oh, have you got it? I was going to say Martin can jump in if you're having issues with sharing slides, but that looks like we're there.
Right, what are you seeing? Are you seeing?
Oh, I'm seeing presenter view. So we've got kind of a timer in the next slide. So if there's a way that you can share screen and show the kind of the presented view rather than that.
Yeah, let me try.
So perhaps if you
Do this.
Yeah, that's the one. Perfect. Thank you, James.
Okay, I might be looking away from the camera because of this, but so I apologise. But
it's okay. We forgive you. Thank you.
Okay, hi everyone. So I'm going to be now talking about something very different to what Trent's been talking about, which is about what we see when we look at the sky at X-ray wavelengths and how it gives us a very different view of the universe. Lets us really see some of the most energetic processes that are going on out there. And in particular, it allows us to track hot gas that's sort of filling some of the largest structures we see across various different across the universe, as well as seeing the processes when matter is falling down into black holes, and that's also getting very hot and it's producing emission that we see by looking at the X-ray sky. But let's just start by going back and thinking about what we see if we look at the visible sky, if we look at it with our normal eyes. Mostly then what we see are stars. So this rather beautiful map I'm showing here is now an image that's been stitched together that's showing us the entire sky. So from both hemispheres, from both north and south, lots of different images taken at different times of year to really stitch together an image of the entire sky. And it's been orientated so that right across the middle here, we're able to see where the band in the center of the Milky Way is. But basically everything that we're seeing here are stars, and stars that are making up the Milky Way as well. So we see many stars all over the place, and then we see this higher concentration of stars down here through the center of this image, which are coming from the Milky Way. You can also see various sort of dust lanes that are blocking some of our views here right into the center of the Milky Way, make it actually harder to see stars in the optical light there. There are a few other things here, such as these sort of clouds here, are the Magellanic Clouds. So these are external small galaxies relatively near to us in galactic terms. We call them dwarf galaxies. They're much smaller than the Milky Way. But that's what we see in our normal optical light. This is only giving us a view of about 10% or so of normal matter that's actually out there and in these stars. So to get a different view, we can try instead look at the sky at X-ray wavelengths. But there's a problem. Unfortunately, for X-ray astronomers, X-rays aren't able to get through the atmosphere. Unfortunate for us as astronomers, but good for us all living on the planet, because X-rays could be quite nasty if they could get to the surface of the planet. And you can see here just an indication of the various different wavelengths we're able to do astronomy at. But you can see there's actually relatively few kind of quite narrow ranges where that light's actually able to get down to the ground, such as the visible wavelengths and then certain radio wavelengths. So if we want to be able to observe at X-rays, then we have to go to space, which means we need rockets. So here's a recent launch of a space-based X-ray observatory. It's called Spectrum Röntgen Gamma. Apologies for the pronunciation for any Germans joining us. It was launched just 2 years ago now in July 2019, so it's one of our newest X-ray observatories. It's a joint Russian and German mission launched here on a Russian rocket. Here's a slightly less recent launch, but I just wanted to show it because it's sort of a slightly different rocket. This was an observatory run by NASA called New Star, and it launched on a much smaller rocket actually, and it's a particularly different type of rocket that actually gets dropped from a plane. So you can see the rocket just being dropped there from the bottom of the plane. New Star was launched at night, but here's another video. This isn't New Star itself being launched, but it's another satellite being launched on the same type of rocket, which gets dropped off the plane. And it's a little scary because you have to sort of hold your breath and wait and hope that the rocket fires to send your very precious observatory up into space. Luckily, in this case, the rocket did fire. That was also the case with New Star. We were able to put it up into space, and that allows us to therefore start seeing the sky at X-ray wavelengths. So here's a selection of some of the X-ray fleet of missions that we now have in terms of our observatories up in space. The two at the top here are really the big observatories that have really been the kind of workhorses of X-ray astronomy now for over 20 years. They both launched in 1999. Chandra is one of NASA's great observatories. It's essentially the X-ray equivalent to Hubble, and it provides us with very high resolution X-ray imaging, very good quality pictures. And here you can see XMM Newton, which is a European Space Agency mission. So XMM stands for X-ray multi-mirror, and you can see that it's actually got 3 telescopes there that lets it collect even more X-ray light. Down here, you've got a couple of these more recent observatories. Swift is a particularly interesting one because it's designed to respond to very rapidly changing sources of X-ray wavelengths as well as for gamma rays. And it goes and quickly tries to follow up and look at the patch of sky where something's kind of going to flash. Spectrum Roentgen Gamma, this mission that we just saw on the rocket being launched, as I said, it's a joint Russian-German mission. And there's actually basically 2 instruments mounted on it. This one that you can see that's slightly smaller on the top, that's called ART-XC. And then there's another telescope called eROSITA that's sitting underneath. And Spectrum Roentgen Gamma is doing something very different. It's constantly scanning the sky. So it's helping us build up a really great new picture of the entire sky at X-ray wavelengths. So it's been up now for 2 years, and it spends every 6 months, it goes around slowly scanning the entire sky and building up a nice picture of the entire sky at X-ray wavelengths. And here we've got New Star. You remember that New Star was that one that was launched from that little rocket that was dropped from beneath the plane. And New Star's quite unusual because it was launched from this small rocket, so it was a very small satellite. But then when it got up into orbit, it has this long extendable beam that comes out and spreads these 2 parts of the spacecraft out. These are the X-ray mirrors that essentially let it focus X-rays. And by having this long distance between the mirrors and the actual detectors, it allows it to focus much higher energy X-rays. So New Star gives us an additional kind of unique view of some of the highest energy X-ray processes. And on the right-hand side here, I'm looking ahead a little bit to the future because it's interesting to think about the mirrors, the facilities that we're having in future. One I'm particularly excited about is called Athena. It's going to be the European Space Agency's next large astrophysics mission. It's going to be this X-ray observatory called Athena. What's unique about Athena is whereas previous X-ray observatories have built their mirrors from metal, which can get very heavy, in Athena we're going to build up the mirrors using silicon, which therefore is much lighter, so we can build a much bigger mirror and we can collect a lot more X-ray light. That will give it much improved survey power, be able to carry out surveys of the sky much quicker than any observatories we've had before, and it also allows you to collect much more light, and it'll have very advanced new instrumentation, for example, that let us measure the energy then of those X-rays that it receives in a lot of detail, and can give us a really detailed and view of the underlying physical processes that's not been possible before. So I'm quite involved in preparations for Athena. I'm very excited about it. There's also Lynx, which is going to be NASA's next observatory. These won't launch until the 2030s, 2034 for Athena, and probably later even for Lynx. So they're a long way off, but it's really exciting to know we have more observatories coming along in the future. Okay, Well, let's go back to thinking about what these observatories let us see. So this was our view of the visible sky, where mostly what we're seeing is the light coming from stars and the Milky Way, so relatively nearby things. And here's a nice new view of the X-ray sky, which has been carried out by this E-Rosetta telescope that's launched on the Spectrum RG satellite. It gives us a completely different view of the sky. Now, this is oriented in the same way, where we're looking at basically a composite image that's showing us the entire sky. And the Milky Way is oriented, so it's this band across the middle here. But we see it very different. And so I'll take you through some of the things that we're seeing when we look up at the X-ray sky. Now, one of the first things you might notice sort of generally in here is that there's this red image, so that the colors in here are representing the energies of those X-rays that we're receiving. So redder colors are lower energy X-rays, and bluer colors are telling us higher energy X-rays. And that energy is also giving us an indicator of the temperature. So red things are slightly cooler, blue things are much hotter, shown in this way. Although with X-rays, we're actually always looking at very, very hot, very energetic processes. So it tends to be sort of millions of degrees centigrade across this different range. So first, what you might see is this sort of red kind of background that's throughout it. That's actually a local bubble, very, very hot. So like I say, sort of millions of degrees centigrade gas, but it's also extremely diffuse. And that's actually comparatively local to where we are. So, within the sort of immediate environment around the solar system, our solar system sits in this relatively big and hot bubble of gas, which is why we see this red light in this X-ray image coming from absolutely everywhere that we're able to pick up using the X-rays. You can see here when we look at the plane of the Milky Way, it's actually you're not seeing so much of the red light. It's a bit darker. That's because there's some intervening kind of gas and dust that's blocking some of that red light, and you start to become overwhelmed as well by all these individual blue sources, which are other processes producing X-rays within our own Milky Way that start to dominate, particularly when you look down here towards the center of the Milky Way. One of the most interesting things, and this was really, to some extent, a bit of an important discovery from E-Rosetta then, is that you see these incredibly large plumes of gas that we're seeing here in the sort of yellow and green colors. And we see this as these sort of hot, somewhat symmetrical structures that we can see coming out from both sides of the plane of the Milky Way here. So these big yellow plumes, you can see it very clearly on this side. You can see it's sort of symmetric. You can also see this big yellow plume here coming out at the bottom here. So this is even hotter gas that's therefore showing up as these yellow and green colors of something like 3 million degrees centigrade. And we think these big plumes are in fact coming out right from the very center of our galaxy, but extending very far out of the plane of the Milky Way. So these are absolutely huge structures. We were just talking about 100 light years not being very far in astronomical terms. But these structures that we're seeing here, we think are about 50,000 light years across. And where on earth does this much hotter gas come from that's actually extending out of the plane of the Milky Way on such large scales? We think there's actually gas that's being heated up and ejected from the Milky Way itself. So coming out from the sort of center of the Milky Way here at some point in the past. So why has that happened? What's happened to sort of heat up gas and throw it out of the galaxy in this way? Well, we actually don't know for certain, but we think there's two possibilities as to what happened. So remember, if we look down at the center of the Milky Way, there's a lot more stars there. And stars during their life, particularly the most massive stars, eventually they end in supernova, where they eject huge amounts of, where they start collapsing in, they run out of fuel, they collapse in on themselves, and in that process they then also end up exploding and sending material back out to very large scales. And so it could be that we had lots of stars down here in the center of the Milky Way, and they got to the ends of their lives, and we had lots and lots of supernova that helped heat up gas and eject it out and shoot it up out to these very large scales that extend right outside the Milky Way. So that's one possibility. Another thing that we think is if we look right down at the center of the Milky Way, we know that there is an extremely massive black hole, so what's known as a supermassive black hole that has a few million times the mass of the sun itself, so the mass of a typical star. At the moment, that black hole is just black, it's very dark, it's not really doing much. But we think that actually at some point in the past, there was material that was being falling on to that black hole right down at the center. And that can actually be a very energetic process. Before the material disappears into the black hole itself, that material can get very hot, and that can actually then send huge amounts of energy as well back out, not from the black hole, but from very close to it. And so we think that it's also possible that, you know, a few million years ago, something like 15 million years ago, maybe this supermassive black hole we have at the center of the Milky Way went through this very active phase where it was growing, and that's what produced a lot of this energy that was sent back out, and essentially inflated these big structures, these large bubbles of hot gas that we see extending out of the plane of the Milky Way. So those are the sort of large structures, but let's also quickly sort of hone in on some of these individual little things. Let's start by looking at this sort of bright spot you can see here. So that's actually a remnant of a supernova, relatively recently. We think it's from about 12,000 years ago, and this is much nearer to us. So this is 800 light years away, so comparatively near. So we're actually able to see the remnant of the supernova itself, and the sort of shells of hot gas is what we're able to see by looking at it in the X-ray. Let's also have another look at something else here. You'll see here's something else that's pointed out as being a black hole. Well, what is this? Cygnus X1. So this is actually what's known as an X-ray binary. So that's where we've got a binary star. We've got two stars that are close together and orbiting around each other. And one of those stars has gone through its life. And at the end of its life, it's gone supernova, and the core has collapsed down. And the core is actually massive enough that what was left collapsed down and we think formed a black hole with a sort of few times the mass of the sun. So it was quite a massive star, forming a reasonably massive black hole, but not anything like the sort of million times scale of the black hole we see at the center of the Milky Way. Well, what we think is happening then in these X-ray binary sources is that some of the material from this star is basically being dragged by the gravity of the black hole. This material is being dragged off the remaining star, and it's falling down onto the black hole, and it's going around and it's getting hotter and hotter before it falls into the black hole. And as this material gets extremely hot, this is now hot and dense, and it can emit large amounts of X-rays, and this is why we have many of these sources that are called X-ray binaries. So this can happen both when we have a black hole left at the center, but also when we have a neutron star as the remnant at the sort of end of a star's life. You can see a few other things around here which are pointed out as being neutron stars. So those are X-ray binaries powered by neutron stars. Over here, I'll point out something called Perseus, which is a cluster of galaxies. So this is now much more distant, and this is actually clusters of galaxies are some of the largest structures we know about in the universe. You can see on the left here an image of this cluster of many different galaxies now, galaxies sort of like our Milky Way, but in some cases much more massive. So there's this large galaxy at the center of the Perseus cluster, which has something like 10 times, it's 10 times larger than the Milky Way itself. But we see all of these galaxies that are closer together in this large cluster, something like 500,000 light years across. But if we look at this cluster in X-rays, and now I'm showing X-rays from Chandra, where we have these really nice high resolution mirrors to look at Chandra, we also are able to see the hot gas that fills these clusters. So this is now a gas of sort of tens of millions of degrees that fills these really large structures, these clusters that we see in the universe. And then lastly, I just wanted to point out one thing that made me not be completely apparent looking at the image, but is the part about this new map of the X-ray sky from Rosita I'm most excited about, which is all these sort of little white pinpricks of light that you can see all over the place here. These are, in fact, there are around 1 million of these picked up across the sky by Rosita, around 1 million point-like sources. Well, what are these? Are these just normal stars? No, not at all. We actually think these are supermassive black holes, so like that supermassive black hole at the center of the Milky Way, but they're in very distant galaxies, and we think these are ones which are actually going through that phase where material's falling onto them, and that material is getting extremely hot and becomes extremely bright. And so when that happens, can in fact, the X-rays that we see from such processes can actually outshine everything else that would be going on in a distant galaxy. So here's an image of a distant galaxy. An optical, it just looks like a galaxy. We see all the stars, but in X-rays, it's completely dominated by a very bright center, which is this black hole, this supermassive black hole now right at the center that's actively growing. And if we go and look at a very small area of sky for a very long time with Chandra, so this is something called the Chandra Deep Field, so it's a small patch of sky roughly covering a quarter of the sky area covered by the full moon. And we see many of these sources. So we see 1,000 in this small patch, something like 500 million. That means that you could actually pick up, if you could do imaging like this over the whole sky. And almost all of these small pinpricks of light that we actually see, we think are growing supermassive black holes, so these very active supermassive black holes in distant galaxies, and very distant, in fact, up to 13 billion light years away. So we're actually able to see this process going on right back across cosmic time. And my own research actually involves using observations like these to try and understand when these periods of time during the life of an individual galaxy take place and why that happens at different times. Okay, so I'll leave you there with just a reminder of what we see when we look at the X-ray sky. So hot bubbles due to the past activity in the Milky Way, remnants from supernovae, binaries with either black holes or neutron stars, these huge clusters of galaxies, and many millions of these active supermassive black holes in distant galaxies. Thanks very much.
Thank you, James. Brilliant. Thanks a lot for that little summary at the end as well. So I think because we've slightly run over time, we're going to I think rather than fielding questions from Brian, if you could just have a little look in the Q&A and just type answers to any that appear in there. Is that okay, James, for the next few minutes?
Yeah.
Thank you very much. So because we have two other speakers to get to, so our next speaker is Avery. So I believe Avery is somewhere in the background. Avery, are you there?
Yes,
Hello.
I'm here. Can you hear me?
Yes, I can hear you. Yeah, and I can see you. Hello, how are you doing?
Great, doing well, thank you.
Good to have you. Have you got some slides to share or anything like that?
Yes, I do. So
yeah, okay, I will hand over to you and
I'll
get
share my
started on your
screen.
talk. Thank you.
All right, so hopefully everyone can see that. Hi, I'm Avery Mikeson.
If you press play for the presentation, yeah, that's it. That looks, brilliant.
I'm Avery Mikeson. I'm a theoretical astrophysicist at the Institute for Astronomy. And I'm going to tell you about some work I did related to COVID-19. Here's an electron micrograph of the little creatures that have been causing all the havoc in this past year and a half. So what, you may wonder, does an astrophysicist have to do with COVID-19? And the answer is that astrophysicists and epidemiologists have something in common, which is that they both use equations in order to model complex situations. And so while I might use equations to model the flow of gas in a galaxy, epidemiologists will use equations to look at the movement of viruses between people that cause an epidemic, right? So we have a similarity in our approaches. And I used that in order to look at a particular aspect of the transmission of COVID-19, right? So to set the stage for that, I want to go back in time to that dreaded period about a year and a half ago, when COVID-19 made headline news, and we began to learn that the virus was no longer only in part of the planet, but has actually landed within the UK. And so this was in all the newspapers. I'm going to draw some headlines from The Guardian. I could have used many other newspapers like The Scotsman or any others, but just to make my job easier, I've only plundered The Guardian and for some choice headlines. And here's some examples going back to February 2020, when we saw the headlines was use tissues and wash your hands. The UK launches a coronavirus public advice campaign, right? So you use tissues so that you don't contaminate somebody else after you've blown your nose, and then you shake their hands. And just in case at all, we should all wash our hands was the advice, so that we don't pick up the virus from somebody else. And even shops started offering free hand washes, as we see this this headline from the Guardian from Lush, and even in red headlines began the debate: which is better, to use hand gel or to just use soap and water to control the spread of the virus. And so the government gave us this advice. It said, wash your hands for 20 seconds, gave us instructions on how to do that. Also wear a face covering so that you don't accidentally cough or sneeze on somebody else. And even if you do cough, keep a distance of 2 meters, because the droplets from the cough should go to the floor, and by then you won't contaminate your neighbor, right? then the headlines started to escalate. And there we have a screaming red headline that says, do we need to wash our groceries? Maybe washing our hands isn't enough. Or in fact, maybe not just our groceries, but anything that's been delivered, all those Amazon packages or packages through the mail, maybe they're contaminated and they were letting them into our home. So maybe we should start washing those down as well. And I know many people who have been doing that and may still well be doing that. And if you're doing it, the advice from the government is just use water. But this became a concern, actually. How do we know that we're not actually importing the virus into our homes? And this is the aspect that I wanted to look at, because so many people at that time were starting to panic over having to wash everything that they were taking into their houses. All right, and there's an interview that actually showed that there could be some issues coming up, that if somebody was at a shop, for example, a customer, and they coughed on an item and then you brought it home, maybe you're bringing the virus home if the person was sick and they didn't know they were sick. Because part of the problem with this virus is that you can be infectious and not have any symptoms for a couple of days. And some people never show any symptoms, so they don't even know they're contaminating something. Or maybe when you're getting a delivery, the delivery person accidentally contaminated the product. So is this actually a concern, is what I'll talk about. And then suddenly things started to shift, actually, which is by July, by the summer of last year, the headline was, does coronavirus spread in the air? And how do we stay safe? And maybe it wasn't actually so much through our hands, but it's actually coming from the air itself. And this is partly because there wasn't any good evidence that it was the contamination was coming through fomites. What's a fomite? A fomite is a substance, an article. It could be a doorknob, a light switch, could even be an article of clothing, something that can actually support the virus. The virus can stay on it and still be viable and transmit the illness to somebody else if they happen to touch that article that's been contaminated. Right, so that's what I'll be looking at, and there was evidence maybe that, well, there wasn't good evidence that this was actually really happening, and so epidemiologists started to back down from the idea that fomites were a real issue, but statistically quantifying this isn't so simple, right? And so by the autumn of last year, the story was changing. No longer were we so worried about washing our hands as we were with wearing face coverings. Okay, so did Johnson get it wrong? Maybe, in fact, we shouldn't have been focusing so much on hand washing, but wearing face coverings instead. And there is even a concern that maybe it's not even just air droplets, but tiny, tiny droplets of air, very small ones that are so small they don't fall to the ground in 2 meters distance, so-called aerosols, that could actually, somebody could cough in a room and it could linger for hours, tiny droplets that somebody else comes into the room, not even knowing that the sick person was there, and they breathe in the droplets. This is actually still an ongoing concern. We still don't know how important that is as a mechanism for transmitting this illness. Okay. So why was there this switch between hand washing to face coverings? Okay, well, what's the evidence for that? So I'll show you a little bit about that, just to give you an illustration of what an epidemiologist does out in the field. And this is an example coming from China on January, February 2020, when they had their first victims of COVID-19. This was done in a hospital. There were 3 rooms that were investigated. 2 of them had already been cleaned before the investigators arrived, and 1 hadn't been. And what they did is look for samples of the virus in the room. And the 2 rooms that had been cleaned, they didn't find any. But here's a 3rd room which hadn't been cleaned yet, and they found the virus was everywhere. And so there was a piece of the flooring that was particularly contaminated and red. There were the yellow dots here are samples that were taken that showed the virus. Other places marked blue here, samples were taken, but they didn't actually detect any virus. And so the conclusion was that, yes, you could actually contaminate fomites through sneezing, coughing, touching, and this might be a way of actually transmitting the illness. But it's not clinching the argument, because the person was sick. If you went into that room, you'd get sick just because the patient had polluted the air, because maybe they had coughed on you or sneezed and you picked it up from there. And so actually showing that you got it from the fomite as opposed to getting it more directly from the sick person is very difficult to demonstrate. And that's why it's so hard to actually show that fomites are a contribution to the spread of any infection. On the other hand, here's another study that was done again in China on the 24th of January, which was Chinese New Year Eve. This was actually one of the problems of how the virus just exploded very suddenly. It's because when it was introduced, it was around the New Year's time in China. And as a result, lots of people were gathering and unknowingly spreading the virus. And this is a case that happened in a restaurant. There was video footage so they could actually see where people were sitting and who was sick and who got sick. So this is showing this person in purple here who was diagnosed with COVID-19 before anybody else. And they were sitting at a table, and there were two other neighboring tables where people got sick afterwards. And they could look at the flow pattern of the air. So investigators went back, they actually put in some marked droplets of fluid to see how they would get blown about. And then they also did some computer simulations, and this is simulation result. So there was on the right side, there were air conditioners, and on the left side, there were vents, but not exhausting all of the air. And so there formed a circulation of air. And what you can see happening is that the table that was downstream from the air conditioner of the sick person, almost all of them got sick, one didn't. And the ventilator, well, it looks like air came back and contaminated a couple other people. If you look actually at the middle table, the two people downstream got sick, people upstream didn't get sick. And this is pretty clear evidence that when you look at the rest of the restaurant, nobody got sick. And the video footage showed that there was no communication. Nobody was passing anything back and forth between these tables. They were all separate groups. It was transmitted by the air. It's pretty clear evidence that air is as a vehicle for transporting the virus. Okay, so that's why there became this emphasis on wearing face covering so as not to contaminate the air. All right, so for the modeling of the possible contribution from fomites, I went back to basic equations that are used to track an epidemic. And this is actually a method that was developed in Edinburgh, as it turns out, by Kermick and McKendrick about 100 years ago, Royal College of Physicians. And the way they formulated the problem is said, let's take a population of people and let's divide them into compartments, into different categories. Okay, so the S category are people who are susceptible to the illness. The E category are people who've now been exposed to the illness, but aren't yet infectious. When they become infectious, that's in the I compartment. And when once in the I compartment, then they are recovered or they are removed, which is a euphemism for unfortunately dying from the population. Okay, so to this model, I added a fomite term. So the infectious people were contaminating fomites. The fomites would then be picked up by a susceptible person who would then become exposed and then infectious and could infect other people, or they could infect more fomites. And so you develop this circulation of fomite infection and infections passing between people triggered by a fomite. So I looked at that to see how important this could be. And the way I did it is to take advantage of something that was pretty unique in the history of controlling epidemics, which was to have large national shutdowns around the world, where we had a lockdown from a rapidly rising. So this light line, dashed line here, is showing the rise in the infection rates per day per person. And at lockdown, they went down. Okay, and so lockdown was quite effective. Now, there are different kinds of folks where this could be important or not. So a case where it wouldn't be important, or where actually the lockdown would be important, is if suppose that the main contribution to the spread was people were in office places and they were touching a light switch and that light switch was contaminating people, or the doorknob to the offices or the office building was contaminating people, then if you have a lockdown, you don't go to work, so you're not getting contaminated, and so the epidemic starts to die down. Okay, so I can't say anything about that kind of fomite, but there are other fomites like the post deliveries or going shopping that wouldn't really be affected by lockdown because people still need their food and they're still getting post, as they have been getting post packages from Amazon, whatever. All right. So it's for that kind of fomite, which people were being concerned about that they had to wash down, could that have been an important factor? And you can see it couldn't be a dominating factor, or the lockdown really wouldn't have mattered because people were still getting their post and still going shopping. And so I tried to constrain that. And this is just a hypothetical model. Let's suppose that about a quarter of the deaths were caused by post. Okay, I'm not saying it was caused by post. Maybe nobody's ever died from any post deliveries. Okay, but let's just suppose that it was a post. Why I picked the post is because actually the post office is so good at quantifying their deliveries, and so it made my job easier to actually understand how to quantify this statistically. Okay. And what I found is that if you have, say, a quarter of the deaths were because of postal deliveries, that would actually, you would only need a few letters of 1,000 delivered to carry the illness, which means it would be very, very difficult to detect. And even of those, only maybe a little over 1% would actually, even if they were contaminated, only a little over 1% would have actually even led to another new infection. And so it'd be very difficult to really follow this item by item. But this is looking at a statistical analysis of the populations to see if we could see an effect like that. So we can't say we see the effect, but we can place an upper limit to how strong it is. And the upper limit actually says that at most a quarter could have been infected this way, led to a death. That doesn't mean it was up to actually at a quarter. It might have been 2%. It might have even been 0.1% or even lower than that. But it's not a primary driver of the infection, and it's well below being a primary driver of the infection is the way it looks. All right. Okay, so that was my little contribution to studying COVID. And what do we learn from this? Well, the first primary lesson is that even if the fomites aren't a primary source of the infection, it's still good practice for general hygiene. Wash your hands before you eat something, before you prepare food for friends or other people. Wash your hands. All right, that's just generally good hygiene practice. As far as food packaging or post, well, okay, so if you look at the government website, they say, yes, this might be a problem. Now, I have to tell you, the post office is really careful about making sure what they're giving you isn't contaminated. Grocery shops, they want you to actually wear face covering in the shop so you don't actually cough on something that somebody else picks off the shelf, right? So these are practices that are done to minimize this kind of a spread. Good idea, but you might, if you really want to be careful, when you come home and you handle your post or you handle your food packaging, when you put it away, by the next day, anything that was contaminated, much that dies away and wouldn't affect you after about a day. In the meantime, after you put things away or open up your post, put it down, wash your hands, and that should be fine. Okay, right? Thank you.
Okay, thank you, Avery. It was interesting to have a slightly different topic in amongst everything else. So thank you for bringing that to us today. Okay, Brian, do we have any questions for Avery?
Not in the Q&A just yet. So as a reminder, people, please do type in your questions. So just a quick one while we're waiting for people to type something in. Avery, how did you come to be helping out with the COVID-19 research?
I got interested in it actually, frankly, through my family. I mean, my extended family, and I have a niece who actually works in public health, and she talked to colleagues of her. And what I found out talking to members of my family around the world is that they all spontaneously snapped into action and started washing down their groceries, and all independently of each other. And I talked to other people and found out that they would let their post sit for a day before they even open it. So this was obviously concern, and you could look on YouTube and you could get instructions on how to do this. So I began to wonder, and my niece was wondering, do we really need to do this? I thought, I know how to quantify that. So I thought I'd give it a go and see how important it actually is.
I guess for anyone watching who's a younger member of the audience, it just shows you that kind of in anything, like if you're learning about maths or statistics at school or college or university, these things can transfer across lots of different disciplines and topics, and they can be useful skills for lots of things in life. So
I think this is a really good example of that, because the basic equation that you could almost translate those equations we use for an epidemic to astrophysical terms. It's really solving the same kinds of equations with the same methodologies and the same way of quantifying the statistics.
Okay, thank you very much, Avery. If anybody else has any questions, still feel free to type them into chat, and we'll type out answers for you. But for now, we should move on to our next speaker.
Thank you very much. Thanks, Brian. So thank you, Avery. So here we have Martin, who's just appeared. So hello, Martin. How are you doing? You're the last talk of the day, of the whole open days. No pressure.
I was doing well till you said that. Now I'm feeling all the pressure now.
I'm only joking. I know Martin well. Don't worry. I'm not being mean to him. So okay, Martin, you are talking to us about ERIS-NIX, a project at the observatory. So a little bit of engineering here, which is brilliant. Okay, so I'll hand over to you if you could share any slides that you have and get started. Thank you very much.
Okay, so hopefully you can see slides now. I'm getting a nod from Fiona and a thumbs up. Excellent, that's working. Okay, well, thank you very much for coming along today and making it here to the very end of the day. Hopefully, I can keep you all awake for this last session. So as Fiona mentioned, this is a bit more talk about the engineering that is done at the observatory, and actually dovetails quite nicely to the first talk we had in the session about exoplanets. So we get a bit of a recap about some of that as well. So there's a series of questions I'm going to go through in this talk. The first one is who? And the answer to that is, well, me. I'm here to talk to you about this today. So who am I? My name is Martin Black. I am an engineer at the UK Astronomy Technology Centre. The UK Astronomy Technology Centre is part of the Royal Observatory, who have, of course, been doing these fantastic open days all weekend. If in the before times, we would have had you here on site, and you would have come to the back lab, the sort of big grey building on the left-hand side of the image that I'm showing just now, which is where we build instruments for the astronomy community of the UK and Europe. And we are world leaders in doing this. If any of you got to dial in earlier on to the Tour of the Moons lab, and a bit of chat about the Moons project, you'll have heard more about this. But for those that you didn't, we build cameras for telescopes all across the world. We're world leaders in doing this. And cameras, instruments, these are the things that astronomers use to collect their data to tell them about the universe and about the science that they research in. The other reason, of course, we're showing this picture is it's just a fantastic view over Edinburgh on a nice sunny day, which today we actually have as well. And it's inevitable that the open days always have fantastic sunshine. And I'm glad to say today has been the same. So we've covered the who. Up next is the what am I going to talk about? And the what in question is this little blue box shown in the photograph. We've got two of my fellow engineers stood there to give you a sense of scale. Now, the blue box itself is called NIX, but the project that I'm talking about is a slightly bigger project called ERIS, of which NIX is part. ERIS consists of three parts. There's an adaptive optics bench, there's the camera NIX, and there's a spectrograph called Sphere as well. I'm going to touch on what a couple of those things are later in the talk. I'm not going to talk about the Sphere spectrograph because that's a bit that we weren't overly involved with. ERIS was a big project, international consortium of different countries. The NIX part of it was primarily ourselves here in Edinburgh, but also involved parts from Switzerland, parts from Germany, parts from the Netherlands, and eventually has gone to be integrated with the rest of ERIS in Germany, and will eventually be going to Chile. So it is really an international collaboration to build this camera. A key step whenever we're building a camera or instrument for astronomers is to ask a very important question, which is why? And ERIS does a number of different science cases, a number of different sort of important things. but the key why for our particular bit of the project was on one particular science case, and that was about exoplanets. Now, unlike Trent's talk at the beginning of this, we're not talking about rogue planets here. What we're talking about is planets going around stars, the kind of normal planets, if you will. This is always a very exciting topic for people. I think exoplanets is very much an attractive sort of thing to talk about because it's something you can relate to. We know about our own solar system, and the idea of there being other solar systems around other stars is quite an accessible, quite a cool concept, and one that has a big link to a lot of traditional sci-fi shows and that kind of thing. When looking for exoplanets are a fairly new science. It's only been around for sort of 40, 50 years now, but there's an awful lot of them out there. There's been a couple of big missions to look for exoplanets. This is the Kepler ROE, or one of the Kepler ROEs, I should say. Kepler was a space mission that went looking for exoplanets and found an obscene number of them. So basically, every single point series of circles shown on that image is a star with a solar system or a planetary system going around it, and all the dots are different planets. So I think at this point it's fair to say that if you see a star in the night sky, chances are it's got planets going around it. And we've discovered these planets through different methods, as was mentioned in the last talk, radial velocity and transit methods being the most common. And the fairly new way of detecting and looking at these exoplanets is direct imaging, taking actual pictures of the planets going around the stars. And this isn't a hugely common thing to do. It's still very difficult, and there's not a huge number of cases. But there's this really nice animation here that hopefully is playing okay for everyone at home. And this is showing you pictures of planets going around another star. Despite working in this field and have done for a long time now, this is still really, really cool. Just the idea that we're looking at these tiny little points of light are other planets going around another star somewhere in our galaxy still boggles my mind. And NICS was going to do a very similar job, taking pictures of these exoplanets, but better than has ever been done before. This is an upgraded camera. This is a new thing to go on to one of the world's biggest telescopes to take better images of exoplanets. Now, that doesn't sound like an easy task, and it's definitely not an easy task. It does raise a question of how do you take a picture of an exoplanet? Now, the obvious answer to that is using a camera like NICS. Here's a schematic view of NICS itself. And you can see there's lots of different parts in there. And given the size of NICS that you saw in the previous slides with Mike and Chris being shown, it's quite a packed full box of tricks that does an awful lot of different stuff. Now, I've only got 20 minutes, so I'm going to try and keep this fairly succinct to go through a few different things in the instrument. So I'm not going to cover all of these in detail of what they do, but I'm going to give you sort of an overview of some of it. Just as a little proof of evidence here, this next slide, there we go, is a picture of the real instrument as well, not just schematics. When we had the instrument open doing some of the final AIT, I managed to catch this image of the parts. But as with so many optical instruments we build, when you're talking about light, you paint everything black to try and reduce reflections, which is great from an optical standpoint, but it really dulls the photographs a little bit. So I'm going to keep using the schematic instead. So to image an exoplanet, we really need three things: a precise image, infrared light, and something to block the starlight. And I'm going to go through to explain a little bit more about each of those things, and then go through and explain how NICS achieves each of those requirements. Starting off with the precise image. Now, inside our camera, we've essentially built the best possible camera we can, using the best lenses we can get, using very tightly toleranced, very carefully designed, manufactured parts, putting all that together very, very accurately, which is a challenge in itself, and there's an entire talk that I could give on that, which I'm not going to do here. But the camera wheel, which is a set of three different camera barrels, so imagine three different lenses for a camera, give you different fields of view, same idea here. An image selector that does some compensation of the amount of light, the distance the light has to travel, just to make sure everything's consistent, and the detector, which is the sensor we use to take the images. Much like in a sort of, if you had a DSLR, for example, a fancy camera, you've got the lens, the mirror system, and then the CCD, the detector at the back. Very similar idea here, just at a slightly different scale than your average camera. Now, we can build the best system in the world, and as might seem slightly arrogant, we probably have done here, certainly in this style. That's great, but there's a problem. When you look up at the night sky and you see stars and stars twinkle, what that does to, first, from an astronomy point of view, is makes an image a bit like this. So this is a picture of Uranus taken through a telescope. Now, it's a bit blurry, and this isn't a problem of the camera. This is a problem of the atmosphere. When light passes through the atmosphere, it gets blurred, essentially. It gets smeared out, and this is because of movements of air molecules in the atmosphere. Now, this is a real problem, and it ruins everything from images from an amateur backyard telescope right through to the biggest telescope in the world. Now, there's two ways of fixing this. One of them is to put things in space, and this is, of course, what Hubble did, and it's one of the reasons James Webb Space Telescope will do it as well. There's more than just that for James Webb, but for Hubble particularly, this was to get around the atmosphere blurring problem. Space telescopes are cool, really, really expensive, so there is another solution. And that's using something called adaptive optics. And that lets you go from an image like this, blurred by the atmosphere, to an image more like this kind of pin sharp where you start to see all the detail. In this case, Uranus will see the spots, but let's take for a star, for example, see those exoplanets, you're going to need that kind of high quality resolution. I'm not going to go into details about how adaptive optics works. Essentially, what you're doing is you're measuring how distorted the light is using some very clever sensors. You're then pushing and pulling a mirror in your system to change the shape of the reflected light to correct for those errors. And then you're doing that continuously, correcting for that many, many times a second to get a flat wavefront or to get a good quality image. As I say, there's an entire talk in that, but I mentioned that ERIS has an adaptive optics bench in it. This adaptive optics bench essentially does this job for us. So by the time the light gets to our camera NICs, the atmospheric distortion, the atmospheric wobble has been taken away, and we've got a nice crisp image for our camera to make use of. Infrared imaging exoplanets in infrared was mentioned in the first talk as well. And this is how we do this kind of job. It's not looking at reflected light, it's looking at light emitted by the planet itself, that kind of heat. I don't have to explain how that works because somebody else already did it for me, which is ideal. But just to remind everyone, when we talk about infrared light, people often think of this, in this case, an example from Formula One, of thermal imaging. It's a very similar sort of idea. Slightly different wavelengths. We're not looking at something quite as hot as this. We're looking at the warm planet in the infrared, but it's the same sort of idea. Thermal imaging is what you can sort of imagine it as. To do infrared imaging like this, our camera has to be cold. And the obvious question everyone asks is, well, why does the camera have to be cold? And the best analogy that I can think of is to think of an image like this. So this is taken from inside a colleague's house with the lights turned off, and you can see out through the window. And this is kind of what you want to do. Our instrument is inside a box, looking through a window at the light coming into it. Now, you want it to be dark so that you can see through that window. If the lights were on, all you would see is this. You're looking at your own reflection coming back at you because the room is light. Now, so the same idea applies here to the infrared. If your room is warm, you would just see the light coming back at you. You see the warmth coming back at you. What you want to do is turn the lights off, i.e. make the instrument cold, and then you can see out and you can see what's going on outside. In the case of NICs, the parts we use to do that are what we refer to as the cryostat, which is essentially the box that goes around the instrument. That's the walls for your room. The vacuum system and cold head underneath as well. And what we have is essentially a large metal box. We take all of the air out of it and then make it very cold. And when I'm talking about very cold, I'm talking about minus 200 degrees Celsius. The reason we have to take the air out is if we didn't take the air out, all of that air would start to turn to liquid, and having a lot of liquid sloshing around inside a box full of electronics and glass and all that kind of stuff, as you can imagine, is a fairly bad idea. So step one, take as much of the air, an extremely high vacuum inside that metal box, and then cool it all down. In addition, we've got some filters in there that filter some more light of the bits we're not interested in. And finally, the detector itself is only sensitive to the infrared wavelengths. So we get rid of any sort of residual optical light that might be getting in, or some of the longer wave heat that might get in by using a certain detector. The last thing that was on that list of image exoplanets was something to block the starlight. Now, I've got a few different images here of directly imaged exoplanets, and in all three cases, you can see a kind of dark spot in the middle. That dark spot in the middle is blocking the starlight. The star is so much brighter than everything else that you wouldn't be able to see the exoplanet if we didn't find a way to get rid of that light. Now, the most obvious way to do this is, I think maybe you shouldn't try at home for safety reasons, but you probably could try, which is if you look at a bright light, you can't see anything behind the bright light. If you stick your arm out, if your hand out at arm's length and stick your thumb across that light, you start to see behind it. And that's the simplest form of coronagraph, which is what we refer to get as something to block the starlight. And that's putting something in the beam to block that starlight. Another example of this would be on this slide, you can see there's a big star. There's also an exoplanet. So your challenge here is to try and spot where the exoplanet is. Good tip here, give your screen a wipe as well, because most of it's probably dust. Everyone spotted the exoplanet now? If I take the star away, does that help? Probably not massively. There, I can assure you, it might not come through on Zoom very well, but we have drawn a still very dark, slightly less dark than the background image of an exoplanet there. So what we have to do inside NICS is get rid of that big bright starlight so we can see that little grey blob next to it. Now, we could do the same idea as some of the other coronagraphs, which is to put something in the way of the beam and to block the light. We're not doing that. We're doing something more clever. And I'm going to try and describe how that clever thing works. And I'm going to struggle to do it because it's very, very complicated. And to be honest, somebody else far smarter than I designed and built this thing, this particular part of the instrument. So I'm going to try and explain it on their behalf. What we've got here is a picture of the star that we're looking at. And we believe there to be an exoplanet around that, let's say. We're going to send that light through a disk of diamond, which has grooves cut in the surface of it. Now, under an electron microscope, it looks like a bit like a record, like an LP or like a CD. And there's this kind of concentric rings of surface, of peaks and valleys, etched into a diamond. That diamond is a few microns thick, so the sort of thickness of a human hair, and the structures on it are that kind of size as well. It's a tiny little thing. And when you shine the light through that, you get diffraction and interference patterns. And what you actually get on your detector camera, your detector system, is something that looks a bit like this. And what you're seeing here is the reference image, or PSF is the fancy word for an image, of the star in the center. And then these two interfered blobs above and below, where you've shifted the light away from half of the star in each case. So this is the same star imaged in at the same time, three different ways. And on the left-hand side, you've got rid of all the excess light for the top image. And in the bottom image, you've got rid of all the excess light on the right-hand side. The way you get rid of that light is by interfering it. If anyone's ever used a pair of noise-cancelling headphones, the way they work is they measure the sort of sound that's around you and then pipe into, through the headphones, the opposite sound, and that cancels it out. It's a very similar process going on here with light. As I say, explaining this is incredibly complicated, and a lot of it, as far as I'm concerned, is magical, but this works, and this works really, really well. And it's a really good way to see exoplanets. That mask that I mentioned, that etched diamond structure, is put inside the aperture wheel of the instrument, is imaged with the camera wheel, the different camera barrels, and then you also got the mask wheel there, which does different kind of masking to get those images. So again, this is where the rest of the parts of that system come in. So you can really see, although NICS is packed with lots of stuff, everything has its purpose. And because we've got multiple mask locations, multiple filter locations, and multiple aperture mask locations, as well as the 3 camera barrels, it's fair to describe NICS as a bit of a Swiss Army knife of an instrument. It has lots and lots of different modes it can be put into. So different ways that you can image exoplanets. There's 2 different modes for imaging exoplanets inside, in fact. And a colleague described it as one of the ways is like having a Lamborghini. When it works, when the conditions are perfect, it's a fantastic car to drive. It's a fantastic mask to use, and we'll get really great images. We've also got an old Ford built into NICS, which is a different type of mask that will work in almost any conditions, so bad weather conditions or high air mass, when you're looking low in the atmosphere with the telescope. It will work in those kind of conditions. So you've got both options there. So you're really trying to do as much as you can with this camera and do as many different science cases and many different options as you can. I alluded to at the beginning of the talk, the last question that I've got, or the second last question that I've got on these slides, and that is the question of where. This camera, obviously, we're not going to keep it in Edinburgh. It wouldn't be a whole lot of use here in Edinburgh. It's currently in Germany, being integrated or put together with the rest of the system. And after that, it's going to these telescopes here. One of these telescopes here. Technically, I think the one on the furthest left, furthest right. I forget which side we're on. And this is the VLT, the imaginatively named Very Large Telescope in Chile, ran by ESO, European Solar Observatories. This is a collection of European countries that run the telescopes based in Chile. And we're going on one of these telescopes to do our science. This is one of the best places in the world to observe from. It's incredibly dry, so you get next to no clouds forming. You get no clouds, which is great as well. You're also very high up, which means you get above the worst of the atmosphere. Now, as I mentioned, ERIS has an adaptive optics system, so we'll get rid of that residual blur. But if you can get over a big chunk of the atmosphere already, you're making your life easier. And that's why you build observatories on mountaintops. And we're going to this observatory, which is the best in the world. Each telescope is just under 10 meters across. The main mirror, main piece of glass on it is just under 10 meters. So you've got one of the world's best telescope with one of the world's best cameras to look for exoplanets. Last question, when? And this is always a slightly contentious question because these projects take a long time, delays happen. If you've ever done a DIY project and you've run into troubles, we have that, the same thing, but much bigger most of the time. And over the last couple of years, we have, of course, had coronavirus, which has caused lockdowns and all sorts of complicated delays. So the current date for delivery of this project will be 2022. We actually might deliver at the end of this year to the telescopes. So it's going to be 2022. But I'm going to add the caveat of probably, because Chile's just reopened its borders to allow international people to come in and come into the country. So we should be able to deliver that this year. But it's all a little bit up in the air. I'm going to assume at some point next year, but I never like to give too many promises. Okay, I think that takes me to the end. So if I stop sharing now, and I can take questions.
Thank you very much. Thanks, Martin. Do we have any questions, Brian?
Yes, we have one question here from Bob, who asks, this is an analogous question to that I asked in the Moon's talk. Is this unit ever going to be used in space?
It's used in space. No, it's not going to be used in space. There are similar systems which you can deploy in space, similar wavelengths or similar sort of ideas. But because we have our adaptive optics system, there's no need for us to go to space. The wavelengths we're looking at, as was mentioned in James's talk, the wavelengths we're looking at aren't blocked by the atmosphere. So there's no, we can do it from the ground. And with the AO system, we can get around the atmospheric problems of distortion. So there's no incentive to put it in space. Therefore, we don't have to worry about all the additional complexity of putting it in space, the additional cost of putting it in space, or have to go through that really nerve-wracking moment where you spend 10, 20, 30 years building one of these things, strap it to a barely controlled firework, and then let it go into space and hope it doesn't blow up, which for my own heart, I'm glad we don't have to do on this project.
Yeah, and one other point I'll add is that when something's in space, you also can't maintain it if anything goes wrong during operation. So it's a lot. Usually you want to avoid going into space if at all possible. It's only certain applications where you have no choice.
Yeah, very much.
So we have one more question from Alec here, who asks, how expensive can a project like this be?
The money question is always a tough one to answer. So in the case of NIX or ERIS, so let me explain. I have project managers who I work with who run the project, and they deal with all the financy stuff, so I don't have to worry about it, which I love. But I think rough number on ERIS is a few million. If I say maybe 5 million or 8 million, it's worth pointing out that the detector in this, there's that one component alone costs about $500,000. So we buy a lot of very expensive parts to do this job. Something like Moons was about 30 million. Something like JWST, you're into the billions very quickly. So these are big numbers, but in the scale of our projects, they're not. And also, it's not just the cost of the parts, but I've been employed for 6 years working on that project. So there's kind of the staff effort and the people power that goes into it as well. So that's the kind of numbers you're talking about, but it's quite hard to put a price on the whole thing.
Brilliant. Thank you so much. Thank you, Brian. I think that's all we've got time for questions. If you do have any other questions, I've popped some information in the chat. So I thought that was the easiest way to share things with you. But we do have a Twitter channel. It's @Royal Obs. So we'll keep an eye on that for a few more minutes. And if you've got any questions, do pop them on there. Other than that, I'd just like to say thank you to Martin for that great talk. Thank you, Brian, for helping out with this event today. And thank you to all the other speakers, which I think have still been watching each other. So yeah, supporting each other. So Avery, James and Trent as well in the background. Thank you very much. Thank you to those of you that are watching, wherever you are. We've really enjoyed bringing you another virtual open days. Hopefully next time we can see you in person next year, but thank you so much for joining us online and for all your great questions. In the chat, I've put some links so that you can find out a little bit more about the observatory. So the first link is just to our virtual Doors Open Day website. We had a new one for this year and there's lots of videos, details about the projects that we've heard about today and the research that's done. So do check that out. That's not going to disappear after today. It's still hanging around. So you can have a look whenever you like. There's a few family activities as well and other things. As I said, do reach out to us on Twitter @RoyalObs. I've popped an Eventbrite link to our organizer page just because we've got quite a lot of different events coming up online. We do lots of talks, longer talks, more in-depth things, and we've got a few events to do with something special called the James Webb Space Telescope, or Webb, which is launching next month. Is it? No, not next month. I've gone a month ahead, December. It's not December yet. So in December, that will be launching into space. So there's some events coming up all about that, so do check them out. And if you want to catch up on any of the events that you've missed this weekend or anything else, there's also a link in there to the STFC YouTube channel. Gosh, that was a lot of information. Sorry, everyone. Just because this is our last event of the weekend, just wanted to make sure that you have all that. So thank you so much for joining us, and I hope we will see you again soon online or in other ways. Cool. Thank you very much. Bye.